Hello everyone, welcome once again. So today on chapter 7, that is estimation. Okay, so when we talk about estimation, it's actually a procedure. And in this procedure, we want to actually find a number that will help us represent, or that will help estimate a population parameter. Or we could also find a range of values that will actually estimate some kind of a population parameter. So that is the idea of this estimation. So in this estimation, we are going to get to know some kind of definitions that comes with it. But before we begin with, we've learned before what it means when we say sample statistics and what it means when we say population parameters. Okay, so these statistics are numerical representation of the sample, and parameters are also numerical representation of the population. Okay, so but in the population for which we have these numerical descriptions, sometimes we don't know the actual value, so we estimate them. So in case you are talking about the population parameter, which is the mu, then we use S bar as an estimate for the mu. When you talk about the population standard deviation, which is the sigma, so let me annotate it so that you get to know. So we have the mu here, we have the sigma, okay? And when you talk about the population proportion, then if you don't know, we use the sample proportion, which is the p-hat, to estimate it. Okay, so you have to know the difference. Okay, so these values that we see, or these numbers that we see, they are numbers, but these are the symbols for it. S bar, S, and p-hat, they are termed as our statistics, and they are the sample statistics, because you get these values from the sample. Okay, but however, it is highly unlikely that the sample statistics that you've seen comes with some kind of error. Okay, they might not give us the actual value that you want. Okay, so there's always an error between the estimated value with the actual value. But our goal is to minimize the error while estimating the population parameters. Okay, all right. So now we know what a sample statistics is, and we know what population parameters are. Okay, so we've actually listed them. All right. So let's get to know some definitions. Okay, so the first definition we want to talk about is the point estimate. Just as we've seen before, the sample statistics, these are point estimates, but we've not actually described them as that because they are single numbers. If you find the mean of some data, you're going to get a single number, and this number will be within a real number. So we call them the point estimate. And these numbers actually help us to estimate what we don't know, which is the population parameter. So the S bar will help us estimate the population mean and the sample standard deviation. So if I annotate them, so we have the S bar here, we have the sample standard deviation, which will also help us estimate the population standard deviation, and the sample proportion, which is the p-hat, will also help us estimate the population proportion. Okay, so these are point estimates. Okay, so this is the first definition we talk about. But the problem with the point estimate is that it gives no indication whether or not the estimate is reliable, because it's just a number to represent. We don't know whether it's reliable. In contrast, then we want to actually consider interval estimation. And why don't we consider a range of values that will help us estimate this population parameter? Okay, so that comes with what? The second definition, the interval estimate. So the interval estimate are a range of values that will help us estimate the population parameter of interest. And in doing so, we will still need the idea of what point estimate. That is why we considered what a point estimate is. So this point estimate will serve as what? The centers of what this interval estimate is. An interval. So we need a center. And within the center, we add an error and we subtract what? An error. So that we create that interval. So this is how it goes. So, but before I move on to that, due to uncertainty, there will exist some errors, but will be limited to some extent, which is referred to as the margin of error. So we marginalize the error. Okay, this interval, we want us to go this kind of error. Okay, so as we said, when getting the interval estimate, we have this point estimate as what? As the center. So if I have this as my center, in case I'm talking about the interval estimate of the population mean, then I'm using what? The point estimate S hat, S bar. When I'm talking about the interval estimate for the population proportion, then P hat will be my center. Are you okay? So now, since assume I'm considering that of the interval estimate for the population mean, so I use S bar, which is the point estimate, as the center. Then I add an error to it, and I subtract an error from it, the same thing. In view of this, I create some kind of interval, and I believe that this interval estimate will estimate our population parameter mu. This is one way of representing it. Since I'm adding and subtracting, then I can simply also write S bar plus or minus E. Okay, this is an error. We will get to know how to find this error. Okay, and also since you are estimating the population parameter, then you're saying that then we can put the population parameter in between them. So less or equal to mu, less or equal to what? S bar plus what? E. Okay, so this is the three ways in representing what? The interval estimate for the population parameter mu. This is for mu. It also applies to the population, other population parameters, okay, in order to estimate them. So if I tell you to find an interval estimate, then this is what I want to see. It's an interval. So this will be your lower bound, and this will be your upper bound. Okay. So the lower is lower than the upper. Okay. So we are going to get some values. One is lower and one is very high. Okay. Okay. So let's move on. So the third thing to consider under this is the level of confidence. So this tells you how confident you think your interval is to be able to estimate the population parameter. So we represent it by C. Okay. Okay. So this is a 1 minus alpha is the probability that the interval estimate contains the population parameter of interest. So alpha is which is the significance level. And we know that when n, if you consider a large sample size, then the distribution of our SY is approximately normal. So you can use the Z table, normal, CDF, and inverse norm. You're going to talk about this later on. So C is our level of confidence, and alpha is what? Our significance level. From the formula, we are saying that C is equal to 1 minus alpha. This implies that if we add alpha and C together by change of subject, if you add C, let me take it here. So if you have C equal to 1 minus alpha, then I can add alpha here. I can also add alpha here. Okay. Then this cancels out, and alpha plus C is equal to 1. If I convert this to 100%, then I'm saying that alpha plus C is what? 100%. Okay. It's either 1 or what? 100%. But normally we use the 100%. Because if I give you C to be 90%, then my alpha, this is my C, then alpha equal to what? 10%. Okay. So this is what we've actually demonstrated here. Okay, so these are the things you them. So always your C is large and your alpha is very small. So when I tell you C is 90, alpha is what? 10. C is 99, alpha is 1. C is 95, alpha is what? 5%, as you see here. Those are the things you see here. All right, I hope you are good. Okay, so let's check this figure. In this figure, we have 40 sample size. Okay, and in this sample size, we have an S bar for each of them. So this S bar is the point estimate, which represents the center of the interval that you're having. So if we've created 40 intervals and we want to calculate a 95% confidence interval for the mean. So this is the population mean. Okay. So we are saying that, okay, if you want to calculate 95% confidence interval for the mean using a sample size of 40, then within this sample size, 38 out of it will contain our parameter of interest, and 2 out of it will not contain the parameter of interest. They will be off from it. Okay, so if you create an interval like this, if I create an interval, so this will be my point, that's the center, it could be my S bar. Okay, so if I create an interval, and this will be my lower and this will be my upper. How do I get my lower? My lower is S minus S E, S bar minus E, and this is S bar plus E. Okay, these are all values. So if you create such an interval 40 times, we are saying that 38 out of it will contain the parameter of interest, and 2. The 2 is what? The 5%. So if you multiply 5% times 40, you're going to get 2. So the 5% is my alpha. So it's some kind of an error that we talk about. Okay. So that is how this interval or this diagram actually represents. If you create 40 intervals, 95, so multiply your 95 by the 40, then it tells you the number of intervals that will contain what our population parameter mu, and the rest wouldn't contain it. So the rest are the ones circled with what? Red. And the blue ones are the right ones. Okay. So there is an interpretation here as well. We interpret it here. Okay, you can check it out. Okay. And one thing to also note under the level of confidence. Okay, so we talk about the last sample, the C is large and alpha is small. And the third thing is that when you are giving the confidence interval, the level of confidence is the area under the normal bell curve in between two z-scores. Okay, so these z-scores tells us how number of standard deviation you have to go off from the center. Okay, when you have the z distribution, the center is what? 0. Okay, so it tells you how the standard deviation you have to go to create some kind of interval. Okay, so if you go some kind of standard deviation of the center of this distribution, then where we shade, that is the middle area, is your C, is your confidence level, and the rest are what? Are your alphas over 2. Why is it alpha over 2? The area under the curve is 100%. And we know that alpha and C should add up to 100%. But by symmetry, if I divide the center into 2, let me show some example here. So let's say this is my normal. We are saying that everything here is 100%. The area here is 100%. Okay. But if I divide this into 2, this is my center. Then I have 50% here. I have 50 here. Are we okay? Because of symmetry by the normal distribution curve. So that is that. Okay, if that happens, okay, then if I cut here and I cut here, and I'm saying that if here is 95%, then it implies that by symmetry, then I will have 5% remaining. But this 5% should be shared between this area. So we have 2.5% and 2.5%, because all of these should add up to what? 100%. Okay, if I put 5% here, then what would be the area here? It wouldn't make it. It wouldn't actually appeal, or we wouldn't actually get the area that we want to get here. It means that the area is 0. But by symmetry, it implies that the area select here should add up to 5%. Okay. All right. So my alpha, since C and alpha add up to 100%, if C is 95, my alpha is what? So if C is 95, then the alpha left is 5%. If I divide alpha over 2, then I have 2.5%. Are you okay? Then I share it between the other areas. Okay. So there is something that cut off this alpha over 2. So it's a value that will cut off this alpha over 2. So sometimes we have the z alpha over 2, which is a value that will cut off the alpha over 2 area. So we have the left and we have the right. Okay, so the left will be negative and the right will be positive. So if I tell you to find z alpha over 2, I mean that I want to get the positive part. But if you use our calculator, the calculator will give us the negative part. But by symmetry, the values are the same. These values are the same. So if you get the negative, please take the positive part, because I just want z alpha over 2, not negative z alpha over 2. Okay, so I want this value. So we want to know how to find the z alpha over 2. How do you find? It's a value, okay, which cuts off this area off from the normal distribution curve that we see. Okay, so how to find it? First, we know we have to find our C. The C is your level of confidence. You find your alpha. That's the significance level. Then you divide the alpha by 2. Okay. Then you use this in your calculator. That is the inverse norm. Okay, so the inverse norm, this is how we find it. I think it should be here. Oh, okay, so when you hit, okay, let's clear everything here. So if you hit the distribution, so second, then you hit fast, then you go to inverse the three, the inverse norm. So you choose that, it will tell you. So the area is alpha over 2. Since you are dealing with z, always mu is 0, sigma is 1, then you paste your answer. So what you're going to change is the area. So the area will be the value the alpha over 2 gives you. If it is 0.025, then you hit the enter, then you paste it, then you take the, so it's going to give you a negative value, which is negative 1.95. If you run it to two decimal places, negative 1.96. But we just want the positive part. So you take 1.96 as your z alpha over 2. So when you have z alpha over 2, so the z alpha over 2 is equal to the negative inverse norm of alpha over 2, 0, 1. Okay. So if you have, this will give you negative, negate it again, it will give you positive, or multiply it by negative 1. Or in case you don't want to, just take the positive part of it, forget the negative that comes in the calculator. Just take the positive part and you are good to go. Okay, so that's how we find the z alpha over 2. Very simple. So we are going to consider some examples on how to find the z alpha over 2. In case you are not using a calculator and you want to use a table, we have a table that also helps us to get the z alpha over 2. So we have the z table. Okay. So z alpha, so in case I give you c to be 95, then my alpha is what? 5%. But we want alpha over 2, so divide the alpha over 2 by 2. Okay, so you divide alpha over 2 by 2, you're going to get 2.5%. If you take it to decimal point, then you're going to get 0.025. So all these you see are probabilities. It could be your alphas. Okay, so we locate 0.025. 0.025. So this is okay. 0.025. Okay. Okay, so this is 0.025 as we see. Okay. So this is the 0.025. Then what to do is that you trace it back. So we are going to trace this back to this. And we trace it back here. So we locate 1.96. So we add these values together. 1.96 and 0.06 together. You're going to get negative 1. What? Negative 1.96. Are you okay? This is the same as the answer the calculator gave, but I am just interested in this value. But in case you don't want to get the negative, then what you do is that you do 1 minus alpha over 2 to go to the positive side. So if alpha over 2 gave you 0.025, then 1 minus that will give you 0.975. Okay, so we're going to get the same value. So let's go down. All these are, so we set 0.975, so 0.975 will be here. 0.975. Okay, so this is 0.975. Then we do the same thing. Oh, sorry. So that is that. Then we go this way. So this gives you the positive value. So that is 1.96. Are we good? All right. Okay. So let's go back to our. So this is the way of using the table to also do it. In case you don't have the calculator, this is the way to use the table. So let's find some z alphas over 2 using our calculator. So find a z alpha. So first of all, you determine. So you go back, you determine your c. You determine your alpha. Divide the alpha by 2. You are good to go. So we have the level of confidence is 95. So alpha is what? 5%. level is 95.55, divide alpha by 2.5%. Okay, so now you put if you're using a calculator, then that will be the inverse norm of half over 2, that's 0.025. Then you maintain the 0 and 1, you hit it, then you get your answer. Okay, so you take the positive part, but I want z half over 2, not negative z half over 2. We do the same for 80%. So the same idea is what we're going to do for all, but with a rule of thumb, all the z half over 2, you can get the answers here. If you have this in mind, you don't have to calculate it again. So if you have 80% confidence level, then our z half over 2 is 1.28. Okay, in case you are rounding it to 2 decimal places, 1.28. Okay, or 3 decimal places is 1.282. Okay, if you take this 90%, we have, if you round it to 3 decimal places, 1.645. Okay, if I give you a level of confidence which is 95%, your z alpha will be 1 point. So this one we just did it. So it's clear, 1.959. But if you round it to 2 decimal places, that will be 1.96. Okay, if you have 99, it's 2.576 if you want to round it to 3 decimal places. Okay, so that is that. So if you have these values in mind, then you don't need to calculate the z alpha. You just punch in what the answers. But if you don't have them in mind, then you can actually use your calculator or the table to get it. So this is how we calculate for z alpha over 2. And what you notice that as our c increases, the z alpha is also what decreases. As our c decreases, the z alpha also what decreases. So if I have c to be 99, this is my z alpha. If I decrease to 95, my z alpha decreases. If I decrease to 90, my z alpha decreases. If I decrease to 80, it decreases. So that is that. If I increase, it increases. All right, so vice versa. So you can note that as well. So we do the same. So now you're coming to say section 7.1. So this is the introduction portion of the estimation. I hope for now. So our goal was to find a z alpha. If you get to know the z alpha, then we proceed to find an a, so that we add the a to a point estimate and subtract from a point estimate to get our interval estimate. All right. So see you in section 7.1. All right. Have a nice day. Bye bye.